In the previous topic, we learned how to calculate the enthalpy change of a reaction using Hess's law. Another way to calculate the enthalpy change of a reaction is from standard enthalpies of formation data. First, it is important for us to understand clearly what standard enthalpy of formation means. The standard enthalpy of formation of a compound is the change in enthalpy when 1 mole of a compound is formed from its pure elements with all substances in their standard states. The standard enthalpy of formation is represented by delta H0 F. The subscript F represents that it is a formation reaction, and the superscript 0 represents that the corresponding reaction occurs under standard conditions. As you can see, the name has 3 parts to this: standard, enthalpy, and formation. Each of these words have specific meaning associated with it. Let us discuss what each of them means. We discussed earlier that the enthalpy of a reaction depends on the conditions under which the reaction is occurring. To maintain consistency, the enthalpy of formation values for various reactions are recorded at a predefined reference condition called as standard conditions. Standard conditions are the following: a constant pressure of 1 atm and a constant temperature of 25 degrees Celsius. So the enthalpy of formation values for all the reactions that we discuss are recorded at these conditions: 1 atm pressure, 25 degrees Celsius. Next, let us discuss what are the standard state for chemicals. For an element or compound, its most stable form at standard conditions, that is 1 atm pressure and 25 degrees Celsius, is called as the standard state of that element or compound. For example, the standard state of oxygen is O2 gas because oxygen at 1 atmosphere pressure and 25 degrees Celsius exists as O2 gas. Similarly, the standard state of hydrogen is H2 gas. The standard state of carbon is graphite. Now that we know what are standard conditions and what are standard state for chemicals, let us now learn to write the formation reactions for various compounds. Let us begin by writing formation reaction for water. According to the definition, 1 mole of water must be formed from its elements in their standard states. So, I place 1 mole of water in its standard state on the product side. The standard state of water is liquid water, that is, the most stable form of water at 1 atm pressure and 25 degrees Celsius is liquid state. Next, let us write down the reactants. The water molecule has hydrogen and oxygen atoms. So, on the reactant side, we need to place both hydrogen and oxygens in its elemental form and in their standard state. The most stable form of hydrogen at 25 degrees Celsius and 1 atm pressure is H2 gas. And the most stable state of oxygen under standard conditions, that is 25 degrees Celsius, 1 atm pressure, is O2 gas. Next, we balance the reaction without changing the coefficient of the product, that is water, because by definition we need to form only 1 mole of water. If we balance this equation, we get 1 mole H2 gas plus half a mole of O2 gas gives 1 mole of H2O liquid. This is the formation reaction of water, and the enthalpy change for this reaction under standard conditions is defined as standard enthalpy of formation for water. The enthalpy of formations for several known substances are already recorded and tabulated. These values are available at the back of any regular chemistry textbook. For example, the enthalpy of formation of liquid water is 285.83 kilojoules. Let us do a couple of more examples. Let us write down the formation reaction for methane. Again, according to the definition, 1 mole of methane must be formed from its elements in their standard state. So I place 1 mole of methane on the product side. The standard state of methane is methane gas. A methane molecule contains carbon and hydrogen atoms. So, on the reactant side, we need to place the elements carbon and hydrogen in their standard states. The most stable state of carbon, that is the standard state, at 25 degrees Celsius and 1 atm is carbon graphite. And the standard state for hydrogen is H2 gas. Next, we balance the reaction without changing the coefficient of methane. The final reaction is 1 carbon graphite plus 2 H2 gas forms 1 CH4 gas. The enthalpy change for this reaction is equal to the enthalpy of formation of methane. And if you look at the tabulated value, the delta H0F for methane is negative 75 kilojoules per mole. Let us do one more example. Write the formation reaction for ethanol C2H5OH. Again, according to the definition, 1 mole of ethanol must be formed from its elements in their standard states. So, I place 1 mole of ethanol on the product side. An ethanol molecule contains carbon, hydrogen, and oxygen atoms. So, on the reactant side, we need to place all these elements in its elemental form and in their standard states. The standard state of carbon, as discussed earlier, is carbon graphite. For hydrogen, it is H2 gas, and for oxygen, it is O2 gas. Next, we balance the reaction without changing the coefficient of ethanol. So I'm going to make 2 carbons on the reactant side. We have 6 hydrogens on the product side, so I'm going to place 3 in front of H2 gas on the reactant side. We have only 1 oxygen atom on the right side, therefore I'm going to place half in front of O2 gas on the reactant side. The enthalpy change for this reaction is called enthalpy of formation of ethanol, and the value is negative 277.38 kilojoules per mole. The standard enthalpy of formation of any element in its standard state is 0 by definition. For example, O2 gas, H2 gas, carbon graphite, all these are pure elements in the standard state. Therefore, their standard enthalpy of formation value will be 0. For example, if we write the formation reaction of oxygen gas like we did it before for ethanol and methane, we need to make 1 mole of these compounds from its elements in their standard states. The given molecule of oxygen has only oxygen atoms. and the most stable state of oxygen at 25 degrees Celsius and 1 atm is O2 gas. So, the given compound is already at its standard states. Therefore, we are not doing any reaction, and the enthalpy change for a non-reaction would be 0. Now that we know how to write the formation reaction for various substances, now we will learn how to use the tabulated standard enthalpy of formation values to calculate the enthalpy change of any given reaction that may or may not occur in the lab. For example, let us consider the following reaction, and we would like to determine the enthalpy change of this reaction without using a calorimeter or doing any sort of experiment. Let us see how we can do that. We learned earlier that enthalpy is a state function. Therefore, the enthalpy change between the reactants and products is always the same no matter what path the reaction follows to get from reactants to products. Let us now define an imaginary path in which all the reactants first transform themselves into respective elements in their standard states and then form products from these elements. Let us now write the reactions for this pathway. Each reactant will be first converted into respective elements in their standard states. This is sort of like writing the formation reaction but in the reverse way. C2H2 gas has carbons and hydrogens. The standard state of carbon is graphite and the standard state of hydrogen is H2 gas. If we balance this, I'll get 2 carbons graphite on the product side and 1 H2 molecule. This reaction is exactly opposite of formation reaction for C2H2. Therefore, the delta H of this reaction would be equal to negative delta H0 F for C2H2 gas. The next reactant is O2 gas. O2 is in its elemental form and already in its standard state. So we don't have to conduct any reaction. Let me just write down 5.5 moles of oxygen gas gives 5.5 moles of oxygen gas. Since there is no reaction that is happening, the delta H for this reaction would be 0. Now all the reactants are converted into their respective elements in their standard states. Let us now convert all these respective elements in their standard states into products. That is, each product will be now formed from the respective elements in the standard states. So the first product is H2O liquid. This will be formed from H2 gas and half O2 gas. If you look at it, this is actually the formation reaction for H2O liquid. Therefore, enthalpy change for this reaction is equal to delta H0 F for H2O liquid. The second product is carbon dioxide, CO2. Let us make carbon dioxide using respective elements in their standard state. Carbon graphite plus oxygen gas combine to form carbon dioxide. We have 2 moles of CO2, therefore 2 moles of carbon combines with 2 moles of oxygen. Now this reaction is 2 times the formation reaction for carbon dioxide. Therefore, the delta H for this reaction is 2 times delta H0 F of carbon dioxide gas. Now, if we add all these reactions up, we get C2H2 gas plus 5.5 moles of oxygen gas to give 1 mole of water and 2 moles of carbon dioxide, which is exactly the reaction that we wanted. Now, according to the Hess's law, the enthalpy change for the overall reaction is equal to sum of enthalpy changes of all the reactions that we added. Let me write that equation in the next slide. So, the delta H naught of overall reaction is equals to the delta H for the reaction 1 plus delta H for reaction 2 plus delta H for reaction 3 and delta H for reaction 4. The delta H for reaction 1 is nothing but negative delta H naught F for the C2H2 gas. The delta H for reaction 2 is 0, but I am going to write this as negative delta H naught F for oxygen gas. Since oxygen gas is in its elemental form and standard state, its value anyhow is going to be 0. The delta H for the reaction 3 is equal to delta H naught F for H2O liquid, and the delta H for reaction 4 is equal to 2 times delta H naught F for carbon dioxide gas. I can simplify this reaction and express it as delta H naught of this reaction is equal to the summation of delta H naught F of all the products minus summation of delta H naught F of all the reactants, where the products are water and carbon dioxide and the reactants are C2H2 and oxygen. We can apply this formula for any reaction to determine its enthalpy change. Next, we can look at the tabulated values to find delta H naught F of C2H2, O2, H2O and CO2 and plug in the values in this equation to determine the delta H naught of overall reaction. For any hypothetical reaction, A moles of A plus B moles of B gives C moles of C and D moles of D. The delta H of this reaction under standard conditions is equal to C times delta H naught F of capital C plus D times delta H naught F of capital D minus A times delta H naught F of capital A minus B times delta H naught F of capital B. That is the delta H naught F of all the products minus delta H naught F of all the reactants.